Okay, we started off discussing what's a one-to-one function. The reason being we wanted to talk about inverse functions. Why did we want to talk about inverse functions? So that we could discuss exponential functions and then their inverses, logarithms. And then we spent a while learning what are the properties of exponential and logarithmic functions, how do we solve them. Finally, we can talk about applications. So in this section, financial applications of exponential and logarithmic functions. So there's something called the future value and present value of money. And this is a really important sort of concept to get a handle on. I know a lot of people in this course are hoping to study accounting at the School of Business, in which case this is tremendously important. You may just want to have money at some point, in which case this is important. You also are going to learn how to calculate what are called rates of return, or determine interest rates to double money. So here is your simple interest formula. Okay. Suppose you borrow an amount of money, which is called the principal and is typically represented with a P. So someone borrows P dollars for T years, and they are charged an interest rate of R. Okay. Then the interest that they have to pay is how much they borrowed times the interest rate times how long they borrowed it for. This is called a simple interest formula, and we are quickly going to leave it behind. But here are a few definitions for some of these financial problems. Annually means once per year. Semi-annually, twice. Quarterly is 4, which is once a quarter. Okay. Monthly, 12 times daily, 365. We ignore the possibility of leap years when we're talking about daily. So here's what happens in the real world. Suppose I borrow $1,000 for 10 years at 5%. Okay. According to the previous formula, at the end of the 10 years, I would just pay a fixed amount. I would pay the $1,000 I borrowed, but then I'd also have to pay back the interest, which would be 5% times 10 years times the $1,000, and I would just say, here you go, here's your money. But that's not how it works. Rather, what happens is, every year you get charged interest, or maybe every quarter or even every day, you get charged interest. And then you get charged interest on your interest if you haven't paid it back. So for example, if I owe you $10 at 10%, after 1 year, I'd owe you $11. Okay, 10% of that. But after 2 years, I would not owe you $12. Because I don't just owe you 10% of the original amount that I borrowed, I owe you 10% of the interest I've accumulated as well. So after 1 year, it was $11. 10% on top of that would actually be $12.1 that I would owe you. And you think, okay, great, an extra dime, who really cares? But when you're talking lots and lots of money over very long periods of time, this starts to become a very, very big issue. Because after then 2 years, I would start paying interest on $12.1, and then I would pay interest on the new total, and then I'd pay interest on that. In this compounding effect, it's called compound interest. Okay. So for an example, suppose a credit union offers 1.5% per year, but it is compounded quarterly on a certain savings plan. What this means is, instead of giving you 1.5% at the end of the year, they're going to split that 1.5% into 4 payments. So there will be 4 payments of 1/4 of the interest. If $2,000 is deposited in such a plan, how much is in the account after 1 year? So suppose there was no compounding. That would just be simple interest. Okay, so I'd have 2,000 plus the interest. The interest would just be the amount I put in there times the interest rate, 0.015, times the number of years, 1 year. And let's see, 1.5% of 2,000 is $30. So if I had no compounding, it would be 2,030. However, what's going to happen is I'm going to get paid some interest after 3 months. 3 months later, I'm going to get interest not just on the money I put in, the 2,000, but also the interest I've already earned, and so forth. So we're going to end up with an answer that's bigger than 2,030. So let's see what it is. Okay. So we're going to use the simple interest formula, but we have to do it multiple times. Okay. So the interest earned is 1.5% times 1/4 of a year, So I've earned $7.50, which means now I have $2,007.50 in the bank. So what happens after another quarter? I earn, again, a quarter period of 1.5%, but now the amount in there is a little bit bigger, and that works out instead of just 750 to be 753. Hooray, 3 extra pennies. So at the end of the third quarter, this is at the end of the second quarter, sorry, the total amount in the bank is going to be 2015. Then I let that sit for one more quarter and I earn this much interest. Again, it's the same interest rate for the same time period, but the amount that I'm earning interest on has grown slightly. So I earn this much. And finally, after one more quarter, I will earn this much interest. So after 1 year, I actually have just a tiny bit more than $2,030. I have an extra 17 cents for my trouble. Okay, so here is a nice formula. Rather than have to do this over and over and over again, there is a nice formula for it. And let's see why this formula works. Okay, so A is the final amount, T is how many years, P is the principal, the interest rate is R, but we are compounding n times per year. Okay, so let's just figure it out for 1 year. So after the first period, I have my original principal, but I have earned interest. How much interest have I earned? The principal times the interest rate times how much of the time period elapsed, 1 out of the n different compounding periods. So I now have P plus PR over n, and if I factor out the P, this is P times 1 plus R over n. So whatever my principal, actually the 1 year doesn't even really matter here. If I have a principal of P, this is what happens after one compounding period. I multiply the amount by 1 plus R over n. So what we've just determined is each compounding period multiply by 1 plus R over n. So suppose there have been 10 compounding periods. What do I multiply by? I multiply by 1 plus R over n for the first period, then by 1 plus R over n for the second period, etc. I keep multiplying by 1 plus R over n. How many periods did I do? 10 of them. So what do I multiply 1 plus R over n to the 10th? Whatever the principal is, after 10 compounding periods, just multiply by this. Now, if you have n times per year at, where is it? At t years, you have n times t total compounding periods to represent, and that's where this formula comes from. Whatever your principal is, p, just multiply by 1 plus r over n to the number of compounding periods, which if you've done n times per year for t years, will be n times t. So for example, you have $2,000 at an annual rate of 8%. Maybe you compound it annually, semi-annually, so twice a year, quarterly, 4 times a year, monthly, 12 times a year, or daily, 365 times a year. So with annual compounding, you just have n equals 1, so this is just r over n, is just r, to the 1. There was only one compounding period because it was 1 year. But suppose you use semi-annual. So now I'm dividing by 2, because that's the number of compounding periods per year, and I'm raising this to the second power, because this is how many times I compounded it. And it works out to be slightly larger than 2160. Well, what if I do it every quarter? 1 plus r over 4th to the 4th gives me even a little bit more. Every month? Well, slightly more, not very much. What if I do it every day? Clearly, gaining interest every day is going to be a massive advantage, right? Barely. Barely changes at all. So we actually saw a pretty significant jump from annually to semi-annually, and then even to quarterly. Quarterly to monthly was a lot smaller, and monthly to daily was barely anything at all. Okay. So what if I said, I'm not compounding every day. What if I did every hour? Then the number of compounding periods would be 365 times 24, because there'd be 24 hours for every day. You know what? I bet the result is 2166.57, maybe. Maybe. It might just still be 0.56. In other words, if I start compounding more and more frequently, the end result doesn't really change much. So imagine not just compounding every hour, but every minute, every second. What if you compounded 4,000 times every second? What if you compounded continuously? You took a sort of limit as the number of compoundings per year went off to infinity. This looks like a much simpler formula, PERT, okay? Compared to P times 1 plus R over N to the NT. This is kind of unpleasant when R and N are decimals or big numbers. And here I just have E, which your calculator can do just fine. And remember remember the definition of E was 1 plus 1 over N to the N as N gets bigger and bigger, which is very, very close to what's happening here as N gets bigger and bigger. There's this extra T and there's this extra R, but that's actually accounted for by these exponents right there, although it's not totally obvious how you get from one to the other. Don't worry about it. I'm just trying to marginally justify why an exponent, E shows up. But if you let the number of compounding periods just run off to infinity, you end up with this exponential equation, which is honestly a lot simpler to work with. So suppose that you took that $2,000 at 8% and compounded it continuously. If I just use PERT, so principal 2,000 E to the RT, 0.08 times 1, we end up with 2166.57. It was basically the same as daily compounding. Okay, so we'll continue with financial applications. Hopefully we've whetted your appetite. You believe maybe that exponential functions have some real-world practical uses.